So, the first talk now for this session this afternoon is by Seiberg, who will talk about recent advances in supersymmetry.
Thank you. I would like to thank the organizers for putting together such a wonderful conference in such a beautiful setting. I also thank the organizers for asking me to give this review talk, and especially because it made me read many papers that otherwise I would not have read, and I'm very happy I did. Furthermore, in the course of preparing this review talk, I've benefited from discussions with many people. This is a partial list, and I would like to thank all of them for that. So I had a daunting challenge that I'll need to summarize literally thousands of papers in one talk, and there's no way I could do that. So I had to make choices which will not be very objective. They will naturally be based on my bias and my preference. So I will not cover everything, but I leave out some topics. But what I will like to make sure is that I'm not overlapping too much with other speakers here. So if there are other topics, if there are some topics which are along the main line of my talk, which are discussed also by others, I'll just skip that and give a reference to the other speakers. So that was another criterion in the choice. Second, I will give many references. At some point, it would look like a long laundry list of topics and references. And yet, I'm sure that I will leave out many references. So I apologize about that, and I hope I will not get too many cite me emails tomorrow morning. So the first thing in creating such a talk, I wanted to find the one-line summary of the talk. One phrase that you will be able to take with you is, okay, that's the main thing that happened. So what I'll do in the next slide, I'll present a one-line summary, and then in the following 3 slides, I'll give you the 3-slide summary, and then if you're not interested, you're welcome to leave, and the rest will be details. So what's the theme? What's different in supersymmetric theories over the last few years, which was not done years before? And of course, such a characterization is never 100% precise, because we leave out some interesting topics, and there were things that I will talk about today which had been discussed before. But nevertheless, I want to make such a short summary. So the theme will be the study of rigid supersymmetric theories, rigid in the sense that there is no quantum gravity. We're not doing string theory or supergravity. We're just doing rigid supersymmetric theory, but we do it in curved or non-trivial space-time. So people have done that before, but I think this has been, in some way, the focus of many of the recent developments. And there are 3 classes of things which come under this category, and I'll list them now, and then there will be a slide per each of them. So what people have found is interesting relations between theories in different dimensions. I'll elaborate on that on the next slide. Second thing is that there were new computable observables in known theories. We can study known theories in non-trivial backgrounds, and that would be another line of development. And these new observables have led to new insights about the dynamics. So now I'm give 3 slides, 1 per bullet here. First, relations between theories. So the old example, which was very popular for many years, is to start with a theory in d dimensions, compactify it on a circle, find a theory in d-1 dimensions, and then see how the dynamics changes as we change the radius of the circle, how the behavior between the d-dimensional and the d-1 dimensional behavior changes, how we interpolate between the two. We have seen this morning another example of that in Witten's talk, where he started from 4 dimensions, and he reduced the number of dimensions by having a boundary. So R4 went to R3 cross R+, which later went to R3, and again gave new insights. Now, over the last several years, starting from the work of Witten in the previous millennium, but following the work of Gayotto, Moore, and Nitsky, and culminating in Gayotto's work, the 6-dimensional 2-0 theory was compactified on various 2-dimensional manifolds to lead to new four-dimensional field theories. And more recently, there was even discussion of compactifying the same theory on a three-dimensional manifold to gain new insights about other three-dimensional manifolds. So this is a very exciting line of development, which I will not pursue here at all, and I'll refer you to these talks. One of them we've already heard today. This is Morozov's talk, but I think we'll hear a lot more about that in Gayotto, Gukov, and Moore later on in the conference, and I'm looking forward to it. Instead, I would like to focus on theories on spheres. So that would be the main thing I'll be talking about. So this is the first point, relations between theories in different dimensions. The second thing will be new computable observables in known theories. So here, the main development that we have seen over the last few years is the work of Pestun, who studied the partition function and correlation functions of four-dimensional theories on S4, and Kapustin, Vialet, Yakov, and many followers. So wherever I have used these ellipses, there are many references, follow up on the original work, which I'm not going to mention here. They studied, again, partition functions and correlation functions in three dimensions. And so this is S4 and S3. But just as we can study just a sphere, we can also study a sphere times a circle. This started with the work of Rummelsberger, who studied S3 cross S1, four-dimensional theories on S3 cross S1. That turns out to be an extremely interesting object, which gives us an interesting index, which I'll explain in more detail later. And Kim, Imamura, and Yokoyama started the analysis of S2 cross S1. And why this is interesting, I will explain later. The third thing that I wanted to mention is new insights about the dynamics. So by putting the theories on non-trivial spaces, we have learned many new insights. First, there were tests of dualities. So Kapustin, Willet, Yakov, and many followers have studied the theory in three dimensions and tested new dualities and tested all dualities and proposed new dualities. And Rummelsberger, Dolan, Osborne, Spiridonov, Vatanov, and many followers tested dualities in four dimensions. So I said it would look like a long laundry list, and in fact it does. The second new insight about the dynamics was the work of Jefferis, who found a generalization of A maximization to three-dimensional theories, and there's a possible connection to a C theorem in three dimensions. That came from studying a supersymmetric theory on S3. There was also a surprising relations between distinct theories in different dimensions, again starting with Gayotto, Moore, and Niecki, the work of Gayotto, AGT, Aldai, Gayotto, Tachikawa, and then a bunch of recent papers, and every day I check the archive, I realize that I have to add another reference here, because this is a hot topic, and I'm sure we'll hear more about it in Gayotto's and Gukov's talk, and we heard about it in Morozov's talks. And finally, relations to integrable systems. And we heard about it this morning, my two talks, Shatashvili and Morozov, and it follows on earlier work of Nekrasov, Shatashvili, Witten, and many others. So this is the three-slide summary of my talk. So now I can go to the outline. If you're not interested in these topics, that's the time to leave. So I'll present some questions. The talk will have three parts. I'll present three main questions, and which will also be the outline of the discussion. So the first question, how do we place a supersymmetric theory on a non-trivial space-time? I got to say that personally, when I first heard about that, I was very puzzled, and I'll explain why. So the first question we would like to ask ourselves, when can we place a supersymmetric theory on curved space? The second, given that we can place a supersymmetric theory on curved space, how do we determine the Lagrangian? Now, the reason I was puzzled is the following. We all know that we can place a supersymmetric theory in anti-de Sitter space. This is very common, and it's been very successful over the last, it's now 14 years or so. But we cannot put a supersymmetric theory in de Sitter space. Everybody knows that. Now, if we go to Euclidean space, we can consider Euclidean ADS, but we might also want to study Euclidean DS, which is the same as a sphere. So on one hand, we know that we cannot put a supersymmetric theory on a sphere. And on the other hand, there is this vast literature about supersymmetric theories on sphere. So what's going on here? So I'll answer this question later in the talk. So this is the first kind of questions. How do we place supersymmetric theories on spheres? The second question is, how do we compute? And we've already seen a preview of what I'll say here in Witten's talk this morning when he talked about localization. And the third question, which is perhaps the most interesting, given that we put the theory on curved space and we managed to compute, what does this teach us? So these are the three parts of the talk, and I'll start with the first, supersymmetry in curved space-time. So the first reaction to when can we put a supersymmetric theory in curved space is that we look for a covariantly constant spinor, or a parallel spinor, a spinor which satisfies this equation. So zeta is a spinor, and it's annihilated by grad mu. There's a slightly more sophisticated answer, which is known as a killing spinor. We look for a spinor which satisfies this equation. Grad mu zeta is some constant c, gamma mu times zeta. And this is clearly a generalization of the first equation, because if we substitute c equals 0, we find the first equation. There's yet another generalization of that, which in order to confuse the readers is also called the killing spinor, where we look for grad mu zeta, gamma mu times another spinor, zeta tilde. This is clearly a generalization of that, because if zeta tilde is c times zeta, this is the same equation. But zeta tilde could be another spinor, which is more general. So for one value of mu, this can be viewed as a definition of zeta tilde, and for other values of mu, these are non-trivial equations. Now, for every one of these, we can also add a background R gauge field, either flat or not, and include it in the covariant derivative. So grad mu can also include a background R gauge field. This comes under the name of twisting and was introduced originally by Witten and has been very powerful. But that's not the most general case. And there are many more examples known in the literature which don't fit this description. In particular, if we look at various supergravity backgrounds, the general equation is of this form. Grad mu zeta is a matrix mu, which has spinor indices. So mu has spinor indices acting on the same zeta, where mu of x is an expression which depends on the various background fields. This could be various forms, which are either in the supergravity multiplet or in the matter multiplet. There could also be various matter fields, gauge fields, and so forth. So this is the most general expression, which is motivated by string theory of supergravity. And I would like to emphasize here a point whose importance will become clear in a moment, is that when we do this analysis in supergravity, we make sure that all the background fields satisfy their equations of motion. Okay, so that's what people have been doing. Oops. We would like to ask the following question. Given a rigid supersymmetric theory, no gravity, how can we put it in curved space? What is this mu of x in the general case when we have an arbitrary supersymmetric theory and we put it in, again, in curved space? We have no dynamical gravity, just the rigid theory. So what is mu of x? How should we think of it? Which constraints should it satisfy? And if we find the solution, and we find the theory in curved space which has such an mu of x, how do we find the matter Lagrangian? How do we use this information to find the curved space supersymmetric Lagrangian? So what is the setup? We start with the flat space theory. It's supersymmetric. It has standard super Poincare symmetry, no local supersymmetry. And we want to put it, say, on a sphere. And then the Lagrangian might be deformed. First of all, it will be deformed because we have to write the metric, various places where we contract indices. But there might also be correction terms which are suppressed by 1 over the radius, 1 over the radius square, etc. Furthermore, the supersymmetry variations of the fields could be corrected. There would be the leading order expression, but there could be higher order corrections. And even the supersymmetry algebra itself could be corrected. The algebra could be deformed by terms of order 1 over the radius square, etc. So how do we do that? The standard approach in the literature is to solve this problem iteratively in an expansion in 1 over the radius. So we start at 0th order with the flat space Lagrangian. We write it in terms of a metric. We just substitute the metric wherever we need to contract the indices. Then we check that the Lagrangian is not supersymmetric. We add correction terms at order 1 over r, both to the transformation laws and to the Lagrangian. And now we check again, it doesn't work. We have to add terms of order 1 over r square to fix it up. And order by order, we fix what we have. So this is the standard approach. And the first thing I want to say about it is that it is very surprising when it works. Not only is it a very tedious and long computation, it usually relies on all sorts of identities that have to be satisfied. Usually multi-fermion terms have to cancel, et cetera, et cetera. The second surprise is that when it does work, surprisingly, it ends at order 1 over r squared. We have this iterative procedure. We find terms at order 1 over r. It doesn't, things look better, but the algebra doesn't close, et cetera. We add terms of order 1 over r squared, r being the radius that we expand in. And then it stops. At order 1 over r squared, we find a nice Lagrangian which works, and we can ask ourselves, why did this happen? So that's what people have done, and here is a summary of the landscape of the various theories for which this is done with the references. I think the first paper I found on the subject is by Bruno Zumino in '77. He studied n equals 1 supersymmetric theories in ADS4. For some reason, at the time, this was called de Sitter space rather than anti-de Sitter space. But don't be confused, that paper is about anti-de Sitter space. So this was really a pioneering work. And he showed that the algebra is the supersymmetry algebra is the supersymmetry algebra in ADS, not the flat space algebra. The algebra was deformed, and the Lagrangian was supersymmetric, and it was derived by Bruno Zumino by precisely this brute force way, kind of fixing everything order by order in the expansion in 1 over the radius. The next thing in historical order is a paper not by Ashok, by Diptiman Sen, a paper which was completely forgotten and probably ignored at the time. It's actually a beautiful paper from '87, who studied supersymmetric theories on S3 cross R. And he did n equals 1, 2, and even higher. Again, the way he constructed the Lagrangian, but to take the flat space Lagrangian and then iteratively adding the terms. And if you try to verify his expressions, it's pages and pages of algebra, but the expressions are correct. This stuff was later derived by Rummelsberger in, I think, the last decade. Then came the work of Peston, who studied n equals 2 on S4. And here we could already ask the question I asked before, how come we can have a supersymmetric theory on S4, even though we don't have a supersymmetric theory in de Sitter space? So maybe we should ask Peston about that, and he will talk about it later in the conference. Then Kapustin, Willet, and Yakov studied n equals 2 on S3, and Kim, Yamamura, Yokoyama studied n equals 2 on S2 cross S1, and here it's easy to generalize to n equals 3, 4, 6, etc. So this is kind of a landscape. And in any one of these cases, people found the Lagrangian on a case-by-case basis using this procedure I outlined earlier. Now, one common thing to all these backgrounds is that they are conformally flat. If you look at them, all of them, they are conformally flat. So it should be relatively easy to put a superconformal field theory on this background. Just write the flat space Lagrangian, it's supersymmetric, perform a conformal transformation to put it on any one of these backgrounds, at least locally, and derive the terms in curved space, and that's what happens. That's all very nice, and indeed, for the case of S3 cross S1, that figured in the work of Kini, Maldacena, Minwala, and Raju, who studied the superconformal index. They took a superconformal theory, placed it on S3 cross S1, so view the S1 as something that gives a trace over the Hilbert space, and that's a state that, and this is a trace which probes various short representations. I'll have some more to say about this later. But it's very puzzling how this construction, which works so naturally for conformal theories, works when the theory is not conformal. Whenever the theory is not conformal, the actual construction of the Lagrangian is very tedious. There's a lot of algebra involved and a lot of room for mistakes. And again, I say that from experience. Furthermore, it's not conceptual. So we can ask ourselves, what's the most general setup? So the clue for finding the answer is that I've always liked to think of every parameter in the Lagrangian as being part of a field. And in the case of supersymmetry, it's not just an ordinary field. Think of it as a background field, and not just an ordinary background field. In the case of supersymmetry, it should be part of a background superfield. So can we recast everything here in terms of background superfields? And the natural parameter that we're talking about is the radius, or the metric. So that naturally leads us to ask, what does all this have to do with supergravity? So I'm going to formulate curved superspace. How do we think first of a theory, ordinary theory, not supersymmetric theory, in curved space? We pick a metric. We write the Lagrangian with that metric. The metric doesn't have to satisfy Einstein's equations. We can take any metric we want and place the theory on that curved space. Now let's add the word super. How do we take a supersymmetric theory and curve it in curved space, or curved superspace? It's straightforward. All we need to do is take a graviton or a supergraviton, including all the auxiliary fields, give them arbitrary values, and put the theory coupled to that arbitrary background. So here is a precise recipe how to do it in steps, like from a cookbook. So we take a supergravity Lagrangian, we write it in superspace. The graviton appears in a multiplet, which has a gravitino and maybe other fermions and maybe some forms and various auxiliary fields and so forth. And I'm going to view all the fields in the gravity multiplet as background fields, classical background fields. I do not satisfy any equation of motion. That's absolutely crucial. Now, here, for the metric, it's obvious that we shouldn't satisfy the equations of motion, because even without supersymmetry, we don't satisfy the equation of motion. We want to put the theory on some curved space, so we find the metric, and we just place the Lagrangian. And we don't have to satisfy Einstein's equations. The novelty of this approach is that we also will not satisfy the equations of motion of the auxiliary fields. This is surprising because usually auxiliary fields in rigid supersymmetric theories are extremely useful, and they simplify computations. But in supergravity, the vast majority of us think that this whole picture with auxiliary fields in supergravity is a big headache, and there are different formulations and compensators, and it's all very complicated. And maybe we don't want to think about it, we just do supergravity in components. The point of view I'll advocate here is different, that what we should, since the graviton, or the metric, is a classical background field, I would like to think of the auxiliary fields also as arbitrary background functions. So curved superspace would be arbitrary metric and arbitrary values for the auxiliary fields, not imposing the equations of motion. So it's clear what needs to be done. We just take the Lagrangian from the literature. We don't need to do any new computation. We take M Planck to infinity. This is good for several reasons. First of all, that makes the graviton, as well as all the auxiliary fields, background fields. No dynamics in gravity. We can specify whatever metric we want. And furthermore, the Lagrangian becomes a lot simpler. Many of the terms and a lot of the complexity of supergravity is simply washed away by taking this limit. So we have to take a certain scaling limit. The auxiliary fields have scaling 1. It's kind of an obvious scaling such that they survive. M Planck goes to infinity, holding the metric fixed. So this is a two-line calculation. And now if we want supersymmetry, all we need to do is impose that the gravitino variation vanishes. And here, this mu of x depends on the metric and the various auxiliary field in the supergravity multiplet. It's absolutely crucial that this mu of x is independent of the dynamical matter fields in the problem. So the cast of characters in our story are various dynamical fields which appear in the Lagrangian. They fluctuate, they're quantum mechanical. And a bunch of classical background fields, obviously the metric. And the novelty is that we have a bunch of fields which are auxiliary in supergravity, but in this case, they're precisely on equal footing with the metric. Oops. So we have to satisfy an equation like that, where this mu of x depends on the auxiliary fields and the metric. And the integrability of this equation, integrability condition, gives us some differential equations for mu of x. And if we can satisfy them, we have a background that preserves supersymmetry. We can preserve 1 supercharge, 2 supercharges, 4 supercharges, and so forth. Furthermore, without doing any additional work, we get the curved space rigid theory. We take the supergravity Lagrangian, we threw away most of the terms by taking M Planck to infinity. And now we just substitute in the metric and the background auxiliary field, and we find the curved space Lagrangian. And again, I can tell you from our own experience, 40 pages of algebra in tech that we had for the various cases were collapsed to half a page. This is a lot easier than the standard approach. So, first of all, this is an enormous simplification, at least technically. If you want to find the Lagrangian on S3 cross S1, this is 2 lines. Second, it makes clear why the iterative procedure stops at order 1 over R squared. The auxiliary fields, So what did we do? We started with some Lagrangian in flat space. We put the metric in. Then the Lagrangian was not supersymmetric. We had to fix it at order 1 over r. The terms of order 1 over r are the auxiliary fields. The auxiliary fields are of order 1 over the radius, so that's what gives these terms. Then the supergravity Lagrangian has terms which are proportional to the square of the auxiliary field. Surprise, surprise, these are the terms of order 1 over r square. And the supergravity Lagrangian does not have higher order terms in the auxiliary fields, and therefore the expansion should better stop. And in fact, it does. So this thing, which was very tedious and quite surprising in the old approach, becomes obvious here. I would like to add another parenthetical comment here, that there are different formulations of off-shell formulations of supergravity with different choices of auxiliary fields. And therefore, all of them are equivalent on shell. But it's very important that we work off-shell. We allow the auxiliary fields not to satisfy their equations of motion, and therefore different formulations of supergravity can allow us to explore different backgrounds. So let's take some examples and see how this thing works. We'll start with ADS4 and S4. ADS4. One quick way of deriving the answers, that's something that was not available to Bruno Zumino at the time, is to add a constant in the superpotential. Take the standard supergravity Lagrangian, add a constant in the superpotential, go to the minimum, decouple gravity, and what you're left with is the rigid theory in ADS4. But from our perspective, we don't even need all that. All we need to do to know is that the supergravity Lagrangian has a scalar auxiliary field, usually denoted by m, and we give it a constant value, 3 over r. The metric is the ADS metric. That solves our supersymmetric conditions, namely the variation of the gravitino vanishes. We take this background, we plug it into the Lagrangian, and we get the Lagrangian in ADS4. That's not that impressive, because after all, if we added a constant to the superpotential, we just find this value to the auxiliary field by using its equation of motion. But where is this thing useful? The first place it's useful is by studying S4. See, this field M is a complex field. So the Lagrangian depends both on M and M bar. So now let's allow ourselves to specify arbitrary values for M and M bar, and think of M as a complex number and M bar an independent complex number, not necessarily its complex conjugate. So if we just substitute M equals M bar equals 3 over IR, so you see this is M equals M bar, so it looks like M is real, but I think of M bar as being an independent field. This thing solves all our equations if the metric is S4, the metric of S4. So note that this is not the standard reality, because M bar is not the complex conjugate of M, and soon this will be important. Equivalently, let's start with ADS4 and take it to Euclidean space. And then the radius appears in various places, and wherever we see the radius, write I times the radius. So all the terms which have R square will simply pick a minus sign. In particular, in the metric, whenever we have an R square, we'll get a minus sign. But the terms proportional to 1 over R will pick an I, and we'll find various funny I's in the Lagrangian. I'll have more to say about them later. Oops. So if the theory is conformal, all the terms of order 1 over R drop out, and everything looks nice. But the theory is not conformal. The terms of order 1 over R are very offensive. The terms of order 1 over R are not real, and the Lagrangian is not Hermitian. More precisely, the Euclidean space Lagrangian is not reflection positive, which means that if we try to take any of the directions on the S4 and turn our S4 into a de Sitter space, de Sitter 4, the Lagrangian will not be Hermitian, and therefore the theory is not unitary. That's reassuring, because we had this puzzle: how can we study theories on S4 when there is no supersymmetry on S4? Well, the statement no supersymmetry in S4 has a fine print that people who proved it for the first time did not bother to tell us, that they assume that the theory is unitary. The statement no supersymmetry in the Sitter space assumes unitarity. If you leave out unitarity, you can put supersymmetry on the Sitter space, except that there are various funny I's in various places. Viewed this way, it's completely obvious. Take the Lagrangian in ADS that we all know and love and stick I in various places. It's clearly invariant under the sphere of this, the symmetry of the Sitter. And it's also clear which terms are going to be the problematic terms. Because for conformal theories, there shouldn't be any puzzle. We shouldn't have any problem putting a conformal theory on S4. And therefore, the answer, if we expand in some mass scale M, the problematic terms should be terms proportional to the mass. And furthermore, we said that only the terms which are proportional to 1 over the radius should be bad. And therefore, we should go after the terms of order m over r. And indeed, now as a check, go to any one of the Lagrangians in the literature on S4, or S3 for that matter, you'll see that all the terms of order m over r do not have good reality properties. Should this bother us? No, if we are interested in the theory on S4 without trying to interpret it as a sensible unitary field theory. If that's our goal, that's fine. If you do want to interpret it as a sensible unitary field theory, that's clearly not okay. But at least we should be aware that there is this pitfall. What are the symmetry groups? Well, the symmetry group is OSP14 that includes 4 supercharges. You see the supersymmetry algebra is not the supersymmetry algebra of flat space. And for Lorentzian ADS4, it has a nice real form, the real form of supersymmetry in ADS. So that's nice. And as always, if we take it to Euclidean space, Q star is not the complex conjugate of Q bar. So Q star is not equal to Q bar. Q bar is an arbitrary supersymmetry generator. But for S4, the situation is a little bit more interesting. See, OSP14 has a bosonic subalgebra SP4, which is locally the same as SO5. And the isometry of S4 is SO5. So if we would like to have nice symmetries, nice supersymmetry for S4, we should pick a real form, which is the compact real form from this SO5, and there is no such real form for OSP14. Another way of saying it, if we look at 2 anti-commutators here, they give us a bosonic generator, which tries to be a rotation of the S4, but the rotation is not a real rotation. This is at the root of the problem of computing using localization in these theories with S4. So with S4, we don't have a Q which squares to 0 or squares to an isometry or to a real isometry. I'll say a little bit more about that later. Related to that is the fact that in ADS4, and therefore also in S4, the superpotential is not protected. So we have a lot of fun using holomorphic controlling the superpotential. It's a very powerful tool to control the theory. That's all very nice in flat space, but this does not work in ADS4 or on S4. This is related to the fact that what we mean by chiral object and non-chiral object get mixed together. And I can say it in a bunch of different ways, but let's leave it like that. So holomorphy is not useful, and we cannot compute much unless we go to n equals 2. In n equals 2, the algebra is OSP24, and therefore it's computable, and you will see the computations in Peston's work. So n equals 1 on S4 or ADS4 is not computable, n equals 2 is computable. Next example is a little bit richer, S3 cross S1. So the first thing is to identify the auxiliary field we have to give a vev to. So we no longer have full rotation symmetry. There's one preferred direction, the direction of the S1. So it looks like the object we need to turn on should be a vector. So there's a vector auxiliary field in the supergravity multiplet. We just turn it into be a constant along the S1 direction. But then Q, the supercharge, is not well defined as we take it around the circle. So if we try to identify points by taking Q around the circle, because of the background auxiliary field, usually denoted by B mu in the supergravity literature, the supercharge Q is non-invariant and we cannot identify it. The only way to make it invariant is to assume that the theory, or to limit the discussion to theories which have a global R symmetry, and then we can turn on a background U1R gauge field to fix the problem with the supersymmetry charge. So this is a way of putting a theory on S3 cross S1. We turn on a certain auxiliary field in the supergravity multiplet, which is constant along the S1. We turn on a U1R gauge field along the same direction. And now it's really 2 lines to derive the Lagrangian, which agrees with the Lagrangian in the literature. The supersymmetry algebra in this case is SU2/1 cross SU2 cross U1. Let's see the bosonic parts. So it has 4 supercharges, which sit in here. The bosonic subalgebra is SU2 from here cross SU2 from here cross U1, the SU2 from here cross the SU2 from here, this is the isometry of S3. And the U1, which gives us the isometry along the S1, is a linear combination of the U1 factor, the R symmetry that we had, and the original time translation. So it's that linear combination which commutes with Q, and it has to commute with Q so that we have this supersymmetry algebra. This and the U1 is multiplying it. In fact, already at this point, somebody could ask me the following question. We have a construction based on background fields. Every twist that we do is always a background field. But the supergravity multiplet has a background gauge field, a background auxiliary field that I used, but does not have a U1R gauge field. If you look at the standard supergravity Lagrangian, the off-shell Lagrangian does not have such a background field. But in this case, so how did I do it? Well, I basically did it by hand. I just threw it in as a flat gauge field. But there's an alternative way of thinking about it. There's a formulation of supergravity called new minimal supergravity. The terminology is quite awful because it's no longer new. And here, there is a U1R gauge field. And more interestingly, there's the vector auxiliary field that we have here no longer exists. Instead, we have a two-form auxiliary field. So in this formulation, we can really use all the fields that we need are in the Lagrangian. And now the background is supersymmetric through the fact that there is non-zero H, which is dB, through the S3. So in this formulation, we have an S3 with non-zero flux for the auxiliary field through the S3. So that's a two-form B. And along the U1, along the S1, we put a holonomy in the U1R gauge field. So this is how we construct S3 cross S1 in this language. And for the expert, I will argue that there is no quantization, neither for the flux of H, not for the flux here, because, and no periodicity, neither periodicity nor that, because we took m Planck to infinity, and the quantization goes with units of 1 over m Planck or m Planck square. But that's not that important. Next example, we're studying n equals 2 with U1R on S3. One way of doing it is simply taking the previous construction and forget the S1. Or we can just think about it as an intrinsic three-dimensional theory, which allows us to add also terms, Simon's terms, and so forth. And again, the flux of H ensures supersymmetry, and the supersymmetry algebra is SU2/1 cross SU2, very similar to what I discussed earlier. The U1R from here is a global symmetry, and the isometry is SU2 cross SU2, which is here. And as in the theory on S4, if the theory is conformal, there is no problem. But if the theory is not conformal, it's not unitary, consistent with the fact that there is no supersymmetry in the zeta space. And again, as in S4, in terms of the characteristic mass scale M in the radius R, the offensive terms are the terms of order M over R. Let's deform the theory. Now that we've put the theory in curved superspace, we can ask what kind of knobs can we turn? What can we change in the theory? And again, I would like to think of every possible deformation as a background superfield, because this will allow us to easily implement supersymmetry. So the obvious thing to do in all these examples, let's think of it as S3 cross R or S3 cross S1, is take any one of the flavor symmetries. The problem has various flavor symmetries, say U1 sub F. F is an index which labels the different flavors. And we can turn on a gauge field along the S1 direction. And that appears as a parameter in the theory. And we would like to interpret what this parameter does and see how it will affect the answers. So again, let me review. We have S3 cross S1, and we have a bunch of parameters, which are constant gauge fields along the U1 for the various non-R symmetries. And since we are being kind of reckless with the reality properties, wherever we turn on a parameter, we should allow it to be an arbitrary complex number. So let's start with the real part. The real part of this constant is quite familiar. The real part of this constant appears and is known in three-dimensional theories as the real mass term. It's called the real mass term. This is a mass parameter in the Lagrangian, which comes from a holonomy of a flavor symmetry around the U1 direction. The imaginary part is new. The imaginary part changes the choice of R symmetry, because I emphasized here the fact that we need an R-symmetry in the story in order to be able to put the theory in this curved superspace. But once we have an R-symmetry, it's never unique. We can always shift the R-symmetry by various non-R symmetries. How do we do that? Well, we turn on a gauge field for U1R along that. So if we want to shift what we mean by the U1R, we also need to add a vector background field, a background gauge field, for the non-R symmetries. So the imaginary part of this constant shifts the choice of R symmetry. So again, the real part is the standard mass term, and the imaginary part shifts this choice. And fortunately, we get some bonus. The partition function is manifestly holomorphic in this combination. So there are two knobs we can change. One is the real mass term in the Lagrangian, and the second is the choice of the R symmetry. And surprisingly, the dependence of the partition function combines these two into a nice holomorphic dependence on this complex number AF. There are also various other deformations we can do to the S3. We can squash it in one of the SU2s or in the other SU2, and we can put various twists, but I will not do it here. What can we tell about the partition function on S3 cross S1? So as I said before, this is a trace over the Hilbert space with various complex chemical potentials. Whenever there is a flavor symmetry, we can turn on it as this background gauge field, which appears as a chemical potential in the trace. And the partition functions depends on all these chemical potentials, or their exponentials, which are called fugacities, and I emphasize that they are complex. Now, Rommelsberger emphasized that in this trace, we really compute an index, and everything should be in representations of SU2/1 across various other things. And SU2/1 has short representations and long representations. So let me contrast that with two things we are more familiar with. First, the Witten index. The Witten index, we take a trace with only -1 to the f. As Witten said this morning, we throw away a lot of information. We only count things which are in very special representations. Everything else cancels out. Here, we count many more states, the states which are in short multiplets of SU2/1. There are tons of them, and they can, in fact, an infinite number. And they can be in various representations of the Lorentz group, of this SU2 cross SU2. They can have various spins, various quantum numbers, and so forth. The other thing I would like to contrast it with is with the conformal symmetry. If the theory is superconformal, people also studied, I gave the reference before, this was Kinney et al., Maldacena, Minwala, and I forget the last author. And in that case, we only study special representations of the superconformal algebra. But in fact, in order to make this an index, we don't need superconformal symmetry, because what it is an index of SU2/1. So it's a tiny bit of the superconformal algebra which is really needed. So this object is an index which depends only on short representations, and it contains a lot of information. I'll give formulas later in the talk. A lot of information about the spectrum of short representation. It doesn't just count the number of bosons minus fermions on one hand, and it doesn't just count all the operators, because that would be a mess. It's just right. It counts a lot of information, so much that it's manageable, but it's barely manageable, as you will see. So this partition function has a lot of nice properties. First of all, it's clearly independent of the parameters of the four-dimensional Lagrangian. Just as the index, we can change various mass parameters and so forth in the Lagrangian. And as we do that, the answer doesn't change because it's an index. Another way of saying it, we can start in short distance, do the computation at short distance, and since the answer is independent of the scale, we get an answer about what the theory does at long distance. So we do the computation in the UV, and we find an answer in the IR. And as a bonus, it's also holomorphic in these chemical potentials. So how should we compute? Well, a preview of that was reviewed this morning in Witten's talk. We use localization. So we have to look for a supercharged Q which squares to 0. And more generally, we want Q squared to be an isometry. and we add to the Lagrangian a term that was not there to begin with, proportional to a parameter t, and then an anti-commutator of q with psi, such that the real part of this is positive, and if q squared is an isometry, psi should be invariant under it. Then the problem we're really interested in is the problem for t equals 0, but the answer is independent of t, and there's some fine print here, which I did not write. And hence, the answer does not change as we vary t. And we can then explore it when t goes to infinity, when it is dominated by the zeros of the real part of this object. So we are interested in this limit. And this limit becomes a PDE, a certain partial differential equation. And then the whole functional integral collapses to the solutions of this partial differential equation and a one-loop determinant around it. So we compute the one-loop determinant around it. And in favorable situations, which are quite common, the whole functional integral collapses to an ordinary integral. So the problem becomes computable. And the way I outlined the computation of the trace for or S3 cross S1, where we do the computation at short distance and we learn what happens at long distance, is really a manifestation of this thing. Now, with an appropriate psi here, the PDE is very simple, and the functional integral and the solutions of the PDEs are just constant fields. And then the integral of the modular space of PDE becomes an ordinary integral. And I'll soon show an example where the complicated integral becomes, the complicated functional integral becomes just a matrix model. These are the only modes which really are relevant in the end. So let me give an example which is rather trivial, but it captures many of the ideas. So this was first done by these three people. So this is n equals 2u1 on S3. So the first line is the Lagrangian we have in flat space. So this Lagrangian will demonstrate many of the things I said before, and in a very concrete case. So this is the photon, f mu nu square. In n equals 2, we also need another scalar. In reduction from 4 dimensions, this scalar is the fourth component of the gauge field. So this is a real scalar in 3 dimensions, sigma. D is the familiar auxiliary field from 4 dimensions, so we get minus d squared. And here we have a photinokinetic term. The first thing we want to do when we put the theory in curved space is sprinkle factors of the metric. So we have to put the root g and contract this mu nu and the index mu here with the metric and put the connection here. That's the easy part. Then I said that one needs correction terms of order 1 over r and 1 over r terms. Sorry, 1 over r and 1 over r square. In the traditional way, it was done iteratively. So these are the two terms of order 1 over r, which would be computed. And this is a correction term of order 1 over r square, which would also be computed. From our perspective, these two guys multiply the auxiliary fields. And indeed, you can recognize this term as being the R current. There's an R current in the problem. I told you that you have to turn on a background gauge field for the R current. That's it. That's the object. And the 1 over R square comes from the auxiliary field square. So this is the Lagrangian. And indeed, the order 1 over R terms are not reflection positive, as I warned you before. In fact, you can see the funny I here, which shouldn't be there in Euclidean space. So this term is offensive, and if you're careful with the reality, this bilinear term also has the wrong I to be a sensible mass term in 3 dimensions. But we don't care because we view that as a tool rather than a way of studying a unitary 3-dimensional theory. Now, the answer is independent of G Young-Mills. I've already emphasized that before. So we're really interested in the limit in the infrared, where G Young-Mills goes to infinity, but instead we'll compute it in the UV, where G Young-Mills goes to 0. So then it's clear which configurations dominate. F mu nu has to vanish, just to be flat. And the equation of motion for D sets D equals I sigma over R, and that has to be constant. Because these three terms, this, and that, combine into a perfect square. And there's actually a deep reason why it's a perfect square, but I will not explain it here. Okay, so the whole functional integral becomes an integral over sigma, and it's computable. So the one-loop determinant is straightforward but tedious, and the whole functional integral is computable. Now, somebody might say that's not a big deal because this theory is really free. This is a quadratic theory. Everything here is quadratic. But there are many generalizations. We can make the theory non-abelian. We can add matter fields. We can add Chern-Simons terms. We can add Wilson loops. and all these things are computable. And in all these cases, the functional integral becomes a matrix model for the field sigma. Sigma is like a vector field. It's a scalar in the vector multiplet. And the whole functional integral becomes a matrix model for sigma. And all the partition functions and correlation functions are computable. So let me mention, without elaboration, computations which were done. Now I'm in the second part of the talk, or the third, where we do computations, and we will soon learn lessons from it. So computations which were done in 4 dimensions, Peston and his collaborators studied Wilson lines and 't Hooft lines on S4 and S2 cross something, and this will be discussed in Peston's talk, so we'll not do it here. On S3 cross S1, which is conformal, it should also be relatively straightforward to put the theory. And beautiful computations which were done by the Stony Brook group, by these people, studied this superconformal index in various n equals 2 and n equals 4. And they exhibit all sorts of miraculous properties, but I don't have time to do that. I would like to say a few words about S3 cross S1 when it's not conformal, because I think that this is an interesting case. Notice that in this case, the theory is unitary. We're unitary because we think of S1 as being time, so we have no problem. The theory is reflection positive. It's only if we forget the S1 and we have a theory only on S3 that we have this puzzle with unitarity. So if the theory is superconformal, there's no problem. This is the superconformal index of Kinney et al. But if it's non-conformal, it's also interesting because it does not depend on the scale, and we can use it to compute using the free field expression. So we take the Lagrangian at short distance, where the theory is free. We're basically doing a free field computation on S3 cross S1. And when we do that, we find the answer, and the answer should be also correct in the infrared. All the standard puzzles in computing the Witten index, which are associated with the 0 modes, which forced Witten to go to the torus and so forth, are not present here because we work on S3. So we do use that or equivalently localization. And this probes, as I said before, all the operators in short representations, not just the chiral ones. So we can compute just the Witten index. The next step in complexity will be all the chiral operators, but here we count all the operators in arbitrarily more complicated representations. And the answers are extremely complicated, really extremely complicated. And in order to demonstrate that, I decided to give a formula here on the next page. So this is an expression from Dolan and Osborne, and it was computing some SUNC with some number of flavors. You can probably not see it from the back, but that's not the point. The point I'm trying to make is that there is a formula. And this gamma is an elliptic gamma function. Let me make some comments about that. Various lessons. First of all, this is an explicit formula. Take the whole functional integral and we get a very explicit formula. Second, the answer is non-trivial. Nobody's going to say that this is trivial. And it uses special functions. In fact, these are special functions which are really newcomers to the set of special functions. Whoops. These are special functions which part was called elliptic hypergeometric series, studied by Frenkel and Touraev. This is really state-of-the-art mathematics. And we can do this computation. I cannot, but these people did. Whoops. These people did. And they did it in 2 different theories which flow to the same infrared fixed point. So this is actually the expression in the electric theory, hence the subscript E here. And they have another expression which is different, looks different, and equally complicated, and it should better be the same. Miraculously, these special functions were studied, mostly by Rains and Spiridonov, and they satisfy all sorts of marvelous identities which make the duality work. Conversely, you could say the duality gives us the rationale for all these special identities. We can also do the same thing in 3 dimensions and study n equals 2 in 3 dimensions on S3 cross S2 cross S1. And in this case, people studied various examples. The first thing to study is ordinary 3-dimensional mirror symmetry. We can compute both S3 or S2 cross S1 partition function. This was done by Kapustin, Willet, and Yakov. And of course, everything works. And again, the expressions are highly non-trivial, and they give us a lot of information about these theories. They also studied this duality, which originally put forward by Aharoni. A variant of it was given by Givon and Kutasov, and again, it works. And this motivated them to put forward other dualities for symplectic groups and orthogonal groups, where K here is the level of the Chern-Simons, and NF is the number of flavors, and NC is the number of colors. So a rich set of dualities was proposed and was tested. The last topic I want to discuss is Z minimization. So consider an n equals 2 theory in 3 dimensions, which has an R symmetry, and some non-R symmetry, U1R, with charges with U1F with charges FF. So if there are no accidental symmetries in the IR theory, we should have a superconformal fixed point, and at this fixed point, there should be an R symmetry there, which must be a linear combination of some random R charge that you picked and the various charges of the non-R symmetries. So in 4 dimensions, these coefficients, A sub f, were determined by a procedure called A maximization of introligator and Wecht. What happens in 3 dimensions? Well, that's the equation we want to study. And we can now explore the partition function, Z on S3, as a function of all these parameters. These parameters we would like to determine. And we recall that, again, these are background gauge fields. This is the imaginary part of this Wilson line around the circle. Now, Jaffery's conjectured that the absolute value of Z is minimized at the correct value of AF. Correct, namely, the one which determines the R symmetry in the infrared. And many tests confirm this hypothesis. So this is an extension of the 4-dimensional A maximization and suggests that there is a version of C theorem in 3 dimensions, and all we need to do is explore the theory on a sphere. And even if we temporarily forget about unitarity, we mess up with unitarity, we should view that as a calculational trick. We are not really interested in this non-unitary theory on S3, except to learn something about the number of degrees of freedom and so forth. So this still needs to be done. So let me summarize. I know I'm a little bit over time. So we saw a rich landscape of rigid supersymmetric theories in curved space-time, and we'll hear more about it in various talks in this conference that I referred to. New theories were found, and many observables were computed. And this has led to a number of new insights about the dynamics of these theories. Many questions which were asked before are now answered, like determining the correct R charge in the infrared. But something much more important in a new topic is not how many questions it answered, but how many new questions can we ask? And I'm alluding here to a comment Chiara made earlier in the conference, and I really sympathize with her. The important progress is that there are new questions we didn't even know how to ask before. And this is not as important, but it is nice to have many new questions which appeared we couldn't ask before. And we all hope that by spring 2012, we'll have the answers to them. Thank you.
So, questions?
2 questions. First, can you put supersymmetric theories on SP times S1 for arbitrary P? So can you take a theory that's supersymmetric in flat space in P plus 1 dimensions and put it on SP times S1 in a supersymmetric way for arbitrary P? Or does it work only in special dimensions?
I know what needs to be done, but I haven't done it. So we've limited ourselves to 4 dimensions and 3 dimensions. I don't know if you're interested in, say, 5 dimensions. I think it would be very interesting to repeat this kind of reasoning for the, say, the 2-0 theory or various 1-0 theories in 6 dimensions. The disadvantage is that we do not have a nice superspace formulation for the auxiliary fields in these theories. So some variant of the procedure outlined here will have to be found. But I think this is an interesting line of direction. But you can also ask about other spaces. I don't know, the 0-2 theory, say, on S2 cross S2 cross S2. I don't know. You see, the standard rules of looking for a covariantly constant spinor are clearly not rich enough to accommodate what can be achieved. So,
one more question, please. In 3 dimensions, if this index is scale invariant, should you be able to compute the ABJM index just by doing a calculation in the free n equals 8 Yang-Mills theory?
3 n equals 8.
The D2 brane theory.
I assume so. In fact, I think I saw a paper the last few days which did that, but I did not have time to read it. So I think the answer should be yes. But anyway, it should be straightforward to just do it.
Okay, one last question.
Is it possible to extend these localization techniques to non-rigid theories? Has it been done? Is it interesting? Or is that something for the future or something that people are looking at?
I don't know the answer, but it's a good question. I don't know the answer.
Okay, thank you.